So we talked a little bit about topological spaces in the last video, but we didn't really get to the connection between topological spaces and graphs. All I did was hint at the idea that if we're going to talk about the drawings, we should understand them in terms of topology. Today we're really going to actually make this connection. What we're going to do is we're going to take a graph and we're going to turn it into a topological space. And we're going to do it in a very geometric way. So it's going to be possible to really just think about it, even though it's not going to look like some weird bending up of a coffee cup into a donut. We're going to really be able to see the graph and immediately see kind of what this geometric object, which we'll think of in terms of topology, what it really is. And then we'll be able to do all kinds of cool stuff with it when you see. So it's called the geometric realization. Right? We're going to take the graph and we're going to kind of put it into Rn. This is not a function here. This is just kind of the concept, right? The graph is going to somehow live in Rn, where n here is the number of vertices, so it's going to be a high-dimensional space. And if at first you might be quite, I think, reasonably uncomfortable with the idea of trying to imagine or think about objects in high-dimensional spaces. But there's one case, I think, where high dimensions becomes quite easy. Is that dangerous to say? Which is in the case of linear algebra, when you're just talking about as a vector space, you can start to imagine just, well, there's a matrix describing linear transformations in that space. So almost everything you do in that high-dimensional space is just analogous to something you might do in the plane or in 3D. So you can think about these high-dimensional spaces. All right, so here's the idea. I'm going to number the vertices. We're only dealing with like finite graphs here, finite vertex sets, so we can just put an ordering on them, and we fix that ordering. Okay, so for a given graph, it has some ordering on the vertices. And what we'll do is we take vertex I, and we're going to map it to the standard basis vector in Rn for I. So it's sometimes called B. It's sometimes called EI, but I didn't want to call it EI because edges are E, and these are really where the vertices are going. So B for basis, and you should think of this again. This is like zeros, and then it has exactly one here in the ith coordinate. So the ith coordinate is 1, everything else is 0. That's the standard basis vector BI. And now the edge EI is going to, or so edge IJ here, is going to get mapped to a line segment between these 2 points. Okay, so I'm going to put the line over it, and that just means line segment, okay? And if you recall, or I'll just say it in case we forgot, you should think of a line segment like this as being the set of all points that you can get by writing it like something like the following: 1 minus t times bi plus t times bj, where t is in the interval from 0 to 1. This is me just parameterizing the line segment. We'll draw a very explicit example right now for a very simple graph. Let's do it for, how about a graph that just has 2 vertices? I'll number them right from the start. It has 2 vertices and it has just one edge, right? Just the edge 0, 1. That's it. Okay. So I'm going to end up drawing this in R2, which is the plane, which is good because it's much easier to draw in the plane than in higher dimensional spaces. And I've got the standard basis vectors B0, B1, and the edge here is going to be this line segment, okay? And again, all the points on here are, you can parameterize them by t as it goes from 0 to 1. And so this would be, this line segment is really the geometric realization of the graph. And so it has this infinite number of points. Even though it's a very simple graph, it was just 2 vertices and 1 edge, as a geometric realization, it has the points all along this line segment. So it has this infinite number of points which is handy for us because it means that we can it becomes a more interesting object topologically. I gave that one example in R2, but there are really not so many interesting 2-vertex graphs. I'll go ahead and say that there aren't any interesting ones. But we're going to end up then with graphs in really high dimensions, right? So if n is really big, here's my hypercube, it's supposed to imply that this is way up in high dimensions. We kind of want to get it down into the plane. This is most of what the drawing will do. We'll also talk about drawing in R3. But we want some kind of mapping, right, that goes from high dimensions down to low dimensions. And we'll get there. And in fact, I'll just spill the beans a little bit. It's kind of a foreshadowing, is that when we talk about drawings, what we really mean, I'll use the future tense here. They will be when we properly define them. They're just going to be continuous maps from the geometric realization. So we're going to take this geometric realization. So we had the graph, which was combinatorial. We get the geometric realization in high dimensions. And then any way you continuously map it down to the plane, we're going to call that a drawing in the plane. All right. But first, I think we need to actually say, in a little bit more rigor, what this geometric realization is. You see, the graph, I've started with a graph here that already has numbered vertices, so it's some numbered vertices and edges. Its geometric realization then is just the basis vector. So this is a collection of points. So this is vertices as points. And this is a collection of line segments. And we're just going to take the union of the whole thing. So this is edges as line segments. This means, right, these are points. If you think of them now living in Rn, and these are line segments in Rn, what we have now is that the geometric realization of the graph is a subset of Rn. If you have a topological space like Rn, and you take a subset of it, you get a topology on the subset as well, where you just take the intersection of an open set with this set is going to be open. And that's good enough, and a lot of the properties of the topology of Rn will be reflected in this subset as well. Okay, so here's the cool fact, though. You know, if you have isomorphic graphs, then their geometric realizations will be homeomorphic. And I think this is kind of not too surprising. If you think about it just a little bit, you can end up with different the different geometric realizations just come from different choices of the coordinates. But there's an asterisk at the end here, which is that the converse of this is not true. All right, so let me say this. Just because if the graphs are isomorphic, then their geometric realizations will be homeomorphic. But you could end up with graphs that have homeomorphic geometric realizations. So when we put them into a geometric space, like they look the same topologically, but they're actually not isomorphic as graphs. And we'll have to see some examples of that. It's not too hard. I could tell you actually what the standard example would just be like a path. Like paths of different lengths are all going to have homeomorphic realizations, but they're not isomorphic. Right? If two paths have different lengths, they're not isomorphic. All right. But here's let's work on the direction where it is true first. So here's the idea. You should think of it this way first. I think if you take an isomorphism, so here's my isomorphism, F, I'll mark it as such, from G to H, I kind of want to turn it into some continuous map from the geometric realization of G to the geometric realization of H. And ideally, if this isomorphism, this one also becomes an isomorphism. You can even think of this, this new function as the geometric realization of F. And this will actually be a very useful idea. So here's how I can do it. I've got this function fv, right? Because if I have a homomorphism, then it gives me a function on the vertices. And since it's an isomorphism, they have the same number of elements. So there's some bijection here from n to n. Bijections like this are permutations. So if it's just a permutation, we can represent a permutation with a matrix, sort of a standard idea. A permutation matrix can be written as follows. So I'll call it P, and the ijth element of the matrix is just going to be 1 if I is fv of j, and it's 0 otherwise. This is a matrix, and if I were to write, say, a single vertex as just its corresponding standard basis vector, it would map it to the standard basis vector that that corresponds to the index change from fv. But that's fine, but I can do something else which is even cooler, which is now that I've written my permutation in matrix form, I can now think of it as a linear function on Rn. Right, and this is a permutation matrix operates on Rn by just changing, in some sense, the names of the coordinates. Right, it changes which coordinates are which, and what we'll see is that, in fact, the geometric realization of f that I wanted is just going to be this permutation matrix restricted to the geometric realization of g. Right? So this is a function on all of Rn, and here I'm just going to restrict it to only apply it to the geometric realization. And in fact, this is going to work, which is pretty great. Something even better is true. But I guess maybe I should hold off before I get there. You see, this f star, which is I'm going to use as shorthand for my geometric realization of f, it is continuous because it's the restriction of a linear map. Right? Linear functions on finite dimensional vector spaces are continuous, and if you take a restriction of one, it's continuous in the subset. So that's a nice continuous function. We do have to check, though, that it really works here. So if I take a point in the geometric realization, then I want to check that it really does map that point into the geometric realization of h. Remember that f was graph homomorphism from G to H. So I really would like to check that the f star really is a continuous function from the geometric realization of G to the geometric realization of H. So let's work it out and just check that it really does what it's supposed to. Again, just a reminder, if I take a point in a line segment, that means I can write that point as this combination, 1 minus t times the first basis vector plus t times the second one for some t in 0 to 1. Okay, this is just writing the line segment parameterized by time. And so when I take f star of x, right, which is just applying the permutation matrix P to x, that's like applying P to this whole thing, 1 minus t times bu plus, oh, I guess this, sorry, this, let's make this w, plus t times bw. Okay, and the wonderful thing about linear functions, in fact, the definition of linear functions is that it's going to distribute over this addition. So I can rewrite this whole thing as 1 minus t times p bu plus t times p bw. Okay, now this permutation matrix was designed to do exactly one thing, which is to take these standard basis vectors and essentially apply fv to them, right? At least to their index. So what that means is that this is equal to 1 minus t times the standard basis vector fv of u plus t times the basis vector at fv of w. Okay, so this is, again, the form of a line segment. this is the line segment between these 2 points. So this is, you can write this as follows. It's in FVU, FVW, this line segment. All right, so I know that if I take any point in the geometric realization, it's sitting on some edge, or it might just be a vertex itself. For isolated vertices, that's maybe the easier case. But if it's sitting on an edge, then it's going to land on some other line segment, and we just have to check that this really is a line segment in the geometric realization of H. Okay, so I could just do that, but you see that this is FVU, FVW. Well, that's equal to, right, FE of UW. That's the definition of FE of UW. And since this is a graph homomorphism, F is, that means that this is in the edge set of H. And so we do really have an edge here, which corresponds to this line segment. So when we mapped x into x through this function, we landed squarely on an edge, the geometric realization of an edge in H. So this is in geometric realization of H. So all of this was just to check that when we did the more or less obvious thing of just trying to permute the vertices, that we actually get a continuous function that maps us from one geometric realization to the other. Okay, because you have to check that your function really does land in the codomain. All right, so, but here's a really important fact. We didn't really need a bijection to define this linear map. It seemed nice because we have this, we could think of them as permutations, but we could have defined the same exact object even if we didn't have a bijection, right? So if I had any homomorphism from G to H, I could define a matrix which is going to give me a linear map. It's going to be a matrix that's going to map me from, I put ng here to and nh to be the number of vertices in G, number of vertices in H. And the definition is basically the same. Mij is 1. Oops, that's a 1, not an I. 1 if I is equal to Fv of J, and 0 otherwise. You can check this, right? So M of Bi, again, is just going to be equal to B Fv of I. Right, so the vertices get mapped by M to the geometric realization of the vertices in G, get mapped to the geometric realization of the vertices in H. And actually, if you go through the arguments in the previous page there, the previous arguments all still apply. So that means it's still continuous and still a continuous function. So really any graph homomorphism has a geometric realization as a continuous map, right? Which is really a powerful idea. All right, if we're going to look at these new continuous maps, we should check certain things about them. One is, this is a nice fact, if I took the geometric realization of an identity map, that is just the identity continuous map on the geometric realization of G. And if I took the geometric realization of the composition of two homomorphisms, I'm going to get the composition of their geometric realizations. Okay, so again, it's saying that somehow this operation plays nice with identity and composition. Okay, so that's these are two facts that are going to be very, very useful for us. Let's see now that we've written all this stuff down, let's look at the proof of that theorem that I started with, which was that a graph is isomorphic to another graph. If this is true, then their geometric realizations are topologically equivalent. That is, they're homeomorphic. And so being isomorphic means that we have two homomorphisms, right, that compose to make identities. It's the definition. And then what we'll get then, because we have the geometric realization of these two graphs, and we have the geometric realization of these two homomorphisms, we just want to check that the composition of these continuous functions, these continuous maps, are going to be identity. So let's check. I'll just do it in one direction. The other direction will be exactly the same. So the geometric realization of G composed with the geometric realization of F. Well, we just checked that, at least we asserted with some confidence and proof by intimidation, that this composition should be equal to the composition, or the geometric realization of the composition. But now we can use the fact that we know that this is the identity on G, implies, again, that this is the identity on the geometric realization of G. Okay, and so the other direction is the same. Right, it's the same for the F composed G. So what we get is that the geometric realization of G and that of H are, in fact, isomorphic. Okay, and we got a very simple short proof of this. Another way to think of this is really that the geometric realization is a kind of graph invariant. That is, remember, we think of graph invariance as some kind of mapping from a graph to some other kind of object, where the two graphs are isomorphic implies that those other objects are equivalent or equal. In this case, equivalence in the topological spaces is homeomorphism. So we're really saying that, yeah, this isomorphism of graphs, G isomorphic to H, implies this homeomorphism of the realizations. Okay, we get this even stronger thing, which is that we get mapping not just between the objects, as the graphs in this case, graphs to topological spaces, but also between the maps, right? So if I have a function, a homomorphism of graphs, I get a continuous function on topological spaces. So when we get this, and it plays nice with identity and composition the way it does, this kind of invariant is called functorial. Hopefully we'll talk just a little bit more about functorial invariance. Okay. So this idea of drawing a graph is really intuitive and pretty simple. And on the other hand, I've wrapped it up in some formalism, which seems a little heavy at first. But work through it, because having a clear idea of exactly what this geometric realization is going to make proving many different facts about drawings very simple to state, very simple to prove. And it gives us a concrete way of understanding not just graphs, but other kinds of objects that we'll see in this class, namely something called simplicial complexes. And so spend the time to work through the definition, really feel like, get comfortable with this. And it's easy to forget that the drawing of the graph is not the graph itself. And when you write down exactly what you mean by a geometric realization of a graph, right, you know that you've changed from one kind of thing, from graphs, to a different kind of thing entirely, topological spaces. And therefore, this idea of sameness, you really know what it means to be the same graph. You have isomorphism of graphs. And then when you have these geometric objects that came from graphs, you really know what it means to be the same there too, because you have isomorphism in the topological category, which is homeomorphism. And so I think This is not actually the first functorial invariant we've seen, but it's the first one I've labeled as such. And I'll let you think a little bit about what other invariants we've seen that might be functorial.